Thank you very much. And thank you all for coming to this talk. As said, my name's Andy Smith. I guess we'll start off.
At this point, something went wrong with the audio feed we got from the mixer desk. It is resolved in about 2 minutes.
Headlines, really cool sounding headlines from the past year or so. So a researcher has cracked RSA 2048 using a quantum computer. Google has just in the past couple of days unveiled this amazing new quantum chip that can perform calculations way quicker than a traditional machine. The Chinese have broken RSA. Okay. But when we pick away the buzz, the hype behind those headlines, it's a little bit less exciting. Yeah, the Chinese did indeed break RSA, a 22-bit RSA. That's a long way from the 2048, the minimum that we tend to be using today. Google's latest chip, you probably saw this in the news recently, that wonderful statistic is based on a kind of pointless problem that doesn't have a real-world application. And the guy that claimed to have broken RSA 2048, I mean, the fact that he claimed to have done it on his mobile phone was maybe a bit of a giveaway that maybe this wasn't a solid break, and yeah, we're still waiting for proof of that. So let's demystify some of this. Let's start off with a little bit of a touch into quantum physics. Not much, but just enough here. Basically, when things get small, they start to get really weird. They start to operate in ways that we just don't expect them to in our macro world. You may recognize some of these phrases if you ever did kind of physics at school, this whole kind of wave particle duality, the fact that small things kind of act as a wave and a particle at the same time. Superpositions, that classic Schrodinger's cat analogy. The cat is both alive and dead at the same time. At the small scales, yes, a quantum thing can be in two different states at the same time, but conceptually makes no sense when we bring it up to the level of cats. And also this kind of quantum process of entanglement, the fact that one particle can be somehow spookily linked to another particle, and if you measure one particle, you cause that other particle to collapse into another predefined state. All really weird stuff. And it turns out that we can use those kind of weird factors of small particles to do some computing. Quantum computing uses those weirdnesses to perform calculations and operations that our traditional computers cannot do. When we talk about a quantum computer, it can sometimes sound a bit like hand-wavy. Quantum computer, the reality is we've got multiple different types or flavors of quantum computer, each using different elements of quantum mechanics in order to do those calculations. The actual calculations themselves are performed on what we call qubits. Again, a phrase that you've probably heard of. These qubits that can be in multiple states at the same time. And we only identify the true state that that particle is in once we take a measurement. The fact that those qubits can be entangled together as well, again, a big driver for some of those really interesting computing functions that our quantum computers can perform. There's two key properties of a qubit, the probability amplitude and the phase. So there's two parameters that gets manipulated when we're undertaking these quantum functions. These quantum functions that are referred to sometimes as gates, gates of type X or Y or S or H or T, like really weird named operations. These are just different ways that we might manipulate that probability amplitude and the alignment of each of those qubits. And this is really fundamentally different to the classic logical gates that maybe we've seen before, things like the AND or the OR gate or the XOR gates, entirely different operations that we are performing on qubits. When we see in the news the fact that a computer has been created with X number of qubits, that's a really easily digestible way of getting a feel for the size and complexity of quantum computers, but it's actually only a very small part of what makes a quantum computer useful. Crucially, we need to have quantum computers with a very, very low error rate. When things get small, they also get affected by noise to a very high degree. So one of the biggest challenges with quantum computers and building quantum computers is being able to control that noise that exists at that teeny tiny level. And actually that was one of the biggest things that most recent chip by Google has done really well. They've made quite a big leap in terms of controlling noise. The other factors that we might consider that drive the usefulness of a quantum computer include how well each of the gates that we're operating on the qubits actually performs the intended function rather than kind of like 90% of the intended function, and also the connectivity between different qubits. These are all lots and lots of different factors that drive the usefulness of a quantum computer. So next time you see a news article that's talking lots and lots about qubits, bear in mind there's a lot more under the hood there as well. Okay, so a bit of a whistle-stop tour through quantum computing. Why do we care about this from a cybersecurity perspective? Well, it turns out that some of those operations that a quantum computer can perform that our traditional computers struggle with are operations that would otherwise break some of the cryptographic algorithms that we use today. Crucial to recognize that a quantum computer isn't just some magical box that you can run normal code on, traditional code on, and it will just accelerate everything. But rather, we need to write a specific function, a specific algorithm that takes advantage of some of those quantum gates, some of those quantum computations. Two of the key quantum algorithms that are of most relevance to us in cybersecurity, Grover's algorithm and Shor's algorithm. Grover's algorithm is an algorithm that allows for almost like brute forcing of a black box function. It is an algorithm that provides a quadratic speed up compared to traditional computers when it comes to things like breaking our symmetric cryptographic algorithms, so things like AES. So to put that into context, normally if you had something protected with AES 128, for someone to be able to brute force that, they would need to go through 2 to the power of 128 operations in order to test all possible combinations and see whether the output matches the target of what they're looking for. With Grover's algorithm, that's dropped down to 2 to the power of 64 operations. So quite a big reduction in the time taken to brute force AES. With Shor's algorithm provides an exponential speed up on things like factoring primes and calculating discrete logarithms. Two mathematical problems that provide the foundation for, unfortunately, all of the symmetric crypto that we tend to use today. So RSA, elliptic curve, Diffie-Hellman, all facing an exponential speed up through the application of Shor's algorithm running on a sufficiently powerful quantum computer. What does that mean in practice? Well, let's take a quick reminder here of, say, something like a TLS session initiation. We've got several different types of crypto involved. The first type is we've got some kind of key negotiation phase at the start of that TLS session. That agrees a session key that is used to then apply some symmetric encryption for that particular session. And typically we also apply a digital signature so that a client side can verify the authenticity of a server side. A few different types of encryption here. The key exchange mechanism and our digital signature, typically using asymmetric crypto, therefore at a large chance of cracking under a sufficiently powerful quantum computer. Our session encryption here, the use of a symmetric cipher, a little bit less of a concern. If we want to improve the security of our symmetric ciphers, we've actually got quite an easy task. We just need to double the length of that key size. So if we want to regain that 128 bits of security for AES, well, we could just use AES 256. Even when faced with a quantum computer running Grover's algorithm, we're still able to retain a decent level of security. Unfortunately, that's not the case with our asymmetric ciphers. Like I say, that's exponential speed up that Shor's algorithm delivers means that we need to do something a bit different. Either we need to use the weirdness of quantum physics to create some kind of new cryptographic system, or maybe we need to find a cryptographic system that operates on our traditional machines that just can't be accelerated through a quantum algorithm. So let's have a look at some of those options. Starting off with some of the quantum technologies, the sort of things that there's lots of vendors out there trying to sell you. Things like quantum key distribution. Quantum key distribution uses those wonderful properties of quantum mechanics in order to get a session key agreed between two parties over an untrusted link in a way that means if there is anyone undertaking any kind of eavesdropping on that connection, we're able to identify that and we can just not use that session key. Usually this uses things like the polarization of photons, things like entanglement between different photons in order to achieve that. Of course, this requires lots of fancy hardware. You can't just undertake quantum key distribution on the laptops and mobile phones that you're using today. Also, bear in mind that the use of quantum key distribution is maybe a little bit limited in that sense. The fact that if we aren't going to be baking in this funky quantum technology into our laptops and our mobile phones, we're typically only going to be able to use QKD on point-to-point links, then that introduces a question on, well, how useful really is that technology? I'm not saying it's completely useless. There are cases where being able to have a quantum secure link today, right now, is valuable, but probably for most organizations and most individuals, going to have limited applicability. The other type of quantum-powered technology in the crypto space that you might have vendors trying to sell you is quantum random number generation. The ability to create random numbers using quantum. And, well, yes, random numbers are important in crypto. We know that, right? But actually, is there anything that wrong with our current random number generation solutions today? Not really. Yes, there are definitely cryptographic attacks that have been successful because someone has not used a sufficiently cryptographically secure random number generator, but that's an implementation error. So again, I caution you around believing some vendor claims that a quantum random number generation is somehow going to solve your quantum crypto concerns. Also bear in mind that neither of these two technologies help us achieve security against the threat of quantum computers breaking things like digital signatures, other forms of public key encryption. Maybe there's something else we need to look at instead. And so this is where I would like to steer you folks towards. The fact that we have quantum-resistant cryptographic algorithms that we can run on our standard traditional computers today, on our laptops, on our mobile phones. Quantum-resistant crypto, drilling home the point here, algorithms that can run on a classical computer. You do not need any funky quantum computer to run a quantum-resistant cryptographic algorithm. The power behind these algorithms are that they are based on mathematical problems where there's no quantum algorithm to speed up the breaking of that encryption. We don't have an equivalent of a Grover's algorithm or a Shor's algorithm that can break these new quantum-resistant cryptographic algorithms. They're just based on a different mathematical problem. You will note the asterisk next to that statement, that we know of today. Sure, who knows, at some point in the future, someone may come up with a cool, funky new way to break some of those new mathematical problems. But today, we feel like they are sufficiently secure. Most of the algorithms that have been going through the selection process that NIST have been running leverage what's called lattice-based cryptography as that hard mathematical problem to give strength to those algorithms. There are a couple of other mechanisms as well that use things like stateless hashing. So we've got a couple of different of those mathematical problems that our post-quantum crypto is being based on. The process that NIST have been running to find some quantum-resistant algorithms been running for a number of years now. Last year, NIST came out and said, here are the first 4 algorithms we're going to standardize. And in the past few months, we've had that standardization process finish for the first 3. So ML-Chem, ML-DSA, and SLH-DSA, the first 3 algorithms that NIST have finalized the standardization process for. You might have seen these algorithms being referred to by different names. The names given to these algorithms as they were working their way through the standardization process are Kyber, Dilithium, and Sphinx. But those were the names that the inventors came up with, and NIST, in a way, just to make things a bit more boring, came up with some definitely far less exciting names. Module lattice-based key encapsulation algorithm. Nice and generic, right? So these are the new algorithms that we should be looking to migrate towards. The NIST website has lots of really great standards documentation that go into a lot of detail on those implementations. Also, for quite a few years, the Open Quantum Safe project has been providing free open source implementations of all of these algorithms as they've been working their way through the standardization process, so that it's given security researchers, crypto analysts, some implementations to be analyzing and exploring with. Now that NIST have actually finally finished the standardization for these first few algorithms, we're starting to see some production implementations as well. And this is really, really cool stuff. The fact that some of these quantum-resistant algorithms are now present in things like Firefox, things like Chrome. Cloudflare have been supporting one of the quantum-resistant algorithms for a good year or so. So it's the sort of thing that we're now starting to be able to get our hands on. And that's why I wanted to give this talk at this point in time, because for a number of years we've been able to talk about post-quantum crypto and say, you should do something. Okay, what should I do? Wait till NIST have made a decision, then do what they say. Okay, we've been waiting. NIST have now finally come out with these standards, so we can start now implementing them and moving towards them. I called out here one of the specific quantum-resistant algorithms supported by Chrome, Firefox, and Cloudflare. MLChem 768, so that's a iteration or a version of the MLChem or Kyber algorithm for key exchange, plus also X25519. X25519. That might sound familiar to some of you. That's one of our elliptic curves. One of those old, classical key exchange mechanisms or public key crypto that we're saying is supposedly broken by quantum computing. What's going on here? Well, this is in fact an example of hybrid crypto. The fact that we are using a combination of both a classical or a traditional algorithm plus also a quantum resistant one. We're effectively encrypting the key exchange twice. What this means is that in an era of a cryptographically relevant quantum computer that can break the elliptic curve part of that key exchange, well, we still have a layer of security provided by MLChem. However, imagine a world where maybe in a year's time, a very smart person comes out with a way of actually breaking MLChem. If that's the only algorithm we're using, then, okay, that's going to be a bad day, week, and maybe even month for us. So, this concept here of hybrid crypto gives us that safeguard, that protection against a cryptographically relevant quantum computer, whilst at the same time providing us with that kind of that comfort blanket, that safety net of a more classical algorithm that's maybe been tried and tested for a longer period of time. And that's not to say that I believe that MLChem or any of these other quantum-resistant algorithms are likely to be weak. I mean, let's face it, they've gone through years and years of analysis. But for those of you that have been following the standardization process, you may have seen the Psych algorithm fall at the last hurdle. That got through several rounds of the assessment and standardization process, only for someone to realize that they could run an algorithm actually just on a laptop computer using some slightly obscure maths from, I think it was the 90s, to break Psych in a surprisingly short amount of time. So again, that's where a bit of that comfort blanket of using more of a classical algorithm along with our quantum resistant algorithm is the way to go, what we call that hybrid crypto. And like I say, this exists today. I was thinking of doing a bit of a live demo, but trying to look behind me at the same time as doing stuff on the screen might have been challenging. But this is a little screenshot that I just took earlier today. This is just the standard version of Firefox, installed on my laptop here, navigating to a particular website that Cloudflare host, and hitting the magic hacking button, F12, to open up DevTools, and taking a look at the TLS handshake. And if we look a little bit closer, we can see the key exchange group for this communication is MLChem 768 plus X25519. So the communication between my laptop here, the using the B-Sides Wi-Fi, connecting to just a random website that Cloudflare is hosting, is actually using a quantum-resistant key exchange algorithm. This stuff is already here. One of the other things I wanted to try to portray today is a little bit of intuition as to how some of these algorithms are operating. If you've ever looked at any type of crypto before, you're probably familiar with the basics of RSA. It's kind of like Security 101. The fact that if we pick two large prime numbers and multiply them together, well, it's actually easy to go in that direction, but it's really, really hard, computationally hard, to take that combined number and then try to derive the original two primes from that. That's the intuition that we have around why RSA is strong. What about lattice-based crypto then? The fact that, this is the type of crypto that many of those quantum-resistant algorithms use. Not all, but many. Most of the time, they're leveraging an algorithm called learning with errors, or LWE. And I really like this because this is quite simple mathematics, really, at the face of it. We create a big long array of equations that follow this format of ax plus by plus cz equals n. A big long array of those. The a's, the b's, the c's, the n's form the public key. The private key is the x, the y, and the z. And it turns out it's really, really hard to derive the values of x, y, and z given the public key for two main reasons. One reason is the fact that there's lots and lots of these equations to try and satisfy those values for, but also crucially, we're adding in a little error, this little error e, into each of those equations. That makes it really, really hard to work out what that x, y, and z are. When I was going through the process of trying to wrap my head around this, I spent a long time diving into lattices. After all, this is lattice-based crypto. Lattices are these big arrays of points in multidimensional space, and there's different ways you could describe lattices, and it gets all very complicated. It turns out that the learning with errors problem doesn't actually use lattices at all. There's no lattice maths in these equations. But what happens is that if you want to try and solve these learning with errors equations, the best way of doing that is to apply some of the same mathematics as we would apply to a lattice-based problem. And so effectively it's equivalent to a lattice-based problem. That's where the term lattice-based crypto comes from in this sense. I've given a very brief overview here of learning with errors. If you want to see a little more about this, some really nice graphical visualizations and kind of worked examples that go into a bit more detail, I really recommend the YouTube channel Chalk Talk Math. They have a really great video around learning with errors, really, really nice demonstration of the mathematics behind that process. Okay, so we have spoken here about what the threat is. We've spoken a little bit about some of the options for dealing with the threat. Let's take some time to talk about the timeline. When should we really start to worry? After all, we know that quantum computers are getting more and more powerful. They're getting more capable. They can perform more operations more reliably with less noise. And at the same time, we've got very smart people doing research to try and make it easier, less computationally intensive, to break some of our crypto. So the point at which a cryptographically relevant quantum computer exists, is created, it's sufficiently powerful to break RSA 2048, is kind of what we refer to as Q-Day. A little bit like D-Day, but quantum day. It's that point where the cryptography that we use today will be broken. Bearing in mind that today quantum computers can only factor pretty small numbers, but yes, the pace of development is fast. Not just about the number of qubits, of course. We need to consider the overall quantum depth of a quantum computer, the amount of noise in that system, and so on. We also need to think about what's referred to as the harvest now, decrypt later attack. The fact that there may not be a cryptographically relevant quantum computer today, but if someone can capture a whole bunch of sensitive information or traffic flowing over our networks now, and then keep that until a sufficiently powerful quantum computer is created, then that can be used to break the data that's being captured today. It's often discussed as a more significant threat than I personally believe it is. The reason being is I take a view from the other side. If I'm an attacker that maybe wants to pull off one of these harvest now, decrypt later attacks, I need to be capturing a lot of traffic. I need to be capturing a lot of data, and potentially for a very, very, very long time, maybe a decade or longer. How practical, how feasible is that? Particularly when you add on the fact that when you're looking at encrypted information, it's all the same. If you're looking at an encrypted packet capture in Wireshark, you can't tell which of the packets are associated with super top secret information versus which of the packets associated with the menu for the Christmas party, right? So in my view, the whole harvest now, decrypt later scenario is absolutely possible, but it will only apply to certain organizations in certain industries. I think also it will apply a lot more to the types of attacks where an adversary is able to identify valuable information even in its encrypted form. So particularly where an organization is using things like encryption on a storage device, or maybe document level encryption. That could be something that allows an attacker to identify what's the really juicy encrypted information. I'm only going to keep a copy of that rather than absolutely everything. I throw out the date here, 2035-ish, question mark, for a cryptographically relevant quantum computer. I mean, that's a massive finger in the air, right? Guess. It's probably not an unfair assessment to use for planning. Particularly given that this is the date that the NSA are using for their post-quantum migration. So the NSA have called out a couple of deadlines, both 2030, 2033, to have migrated off of our traditional crypto and onto quantum-resistant crypto. So, of course, NSA probably have a bit more of an interest in keeping things secret for longer than most of the rest of us. So, yeah, maybe 2035 could be a good date to work to. So it feels like that's a long way off. Why do I need to do anything today? Well, bear in mind that transitioning to new crypto systems is a long, difficult journey. I gave the example earlier of TLS and the various different bits of encryption within TLS, but we use crypto in a whole bunch of other places as well. Things like signing firmware. We use it for digital signatures when it comes to certificate authorities. We have crypto embedded in hardware that maybe doesn't get refreshed or changed, say, only every once a decade or every 2 decades. There's lots of areas where we've got crypto in our world today that is really quite hard to replace. So, my suggestion to you is, as 2025 kicks off, start thinking about what can we do today to start that migration process, given that it will likely take a decade or so. Also want to call out that we are likely to see some additional signals as we go along to help steer whether we need to speed up or whether we could maybe slow down our migration activity. The fact that there are a whole bunch of other uses of quantum computing other than just breaking crypto. So where we start to see those other uses of quantum computing, that's a good signal for either accelerating or slowing down our own migration efforts. So some things to think about. If you are developing software or hardware, I encourage you to think about cryptographic agility. That preparation to change what cryptographic routines you're using inside your software or hardware. Make sure that your cryptographic libraries are kind of pluggable. You can plug them in, you can plug them out. You're not hard coding any key sizes or putting in arbitrary limitations and restrictions into your code or your hardware. For most organizations, you're also going to want to undertake an element of cryptographic inventory to understand what cryptography do you have and where. Who's actually accountable for that bit of crypto in your organization? Asset inventory is one of the most boring things in cybersecurity, but it's also one of the most important, right? And cryptographic inventory it's kind of the same, right? Doing an inventory is not fun, it's not exciting, it's not sexy, but it is the starting point for being able to understand what's my baseline? Where's my starting point? And therefore, how big is that problem space? Where are the assets in my organization that are most sensitive? What's got the most sensitive information? Or what are the assets that if there was a breach of cryptographic integrity, maybe that would cause the biggest impact? Things like financial transactions, of course. And what are the parts of my infrastructure that are going to be the hardest to address? So again, where you've got crypto that's just running on a nice little Windows laptop, that's probably going to be fairly easy to replace. Where you've got that same crypto running on, say, an IoT device, or maybe an industrial control system somewhere, those are devices that, again, might not be replaced for a decade or more. We need to be looking at the range of different types of crypto in terms of encryption in transit, things like TLS, also encryption at rest, things like code signing, digital certificates, whole bunch of different elements of crypto we want to be able to identify. I call out here Zeek as just one free open source example of some tooling that can identify the cryptographic parameters as part of the TLS handshake at the start of a TLS session. And I know, having spoken to some of the folks at the Quantum Village today, that they're also working on some really awesome other open source tooling to help perform some of that cryptographic inventory. So if you haven't already done so, definitely go and have a chat with the Quantum Village on the middle floor today. Another key action is to speak to your vendors. In most cases, certainly where I have done most of my work, a lot of the cryptography that we use is actually part of somebody else's product that we've bought. So it's completely out of our hands to actually do anything about that. We can't go and change that code because it's not our code. But we can work with those vendors and offer some gentle encouragement around, hey, could you please look to upgrade those systems, that software, that hardware, whatever it is. This is something that we can start off with some gentle questions. Maybe then, as the years progress, some more robust questions. Maybe add in some additional requirements. We are only going to continue to buy your software if you have a roadmap that demonstrates how that is going to be quantum resistant, or how that is going to use quantum resistant crypto within a certain time frame, within a certain roadmap. And then again, over time, as that threat starts to increase, we can also increase the level of robustness around working with third parties. Again, I encourage you to think about this because this is a way that collectively we as a industry can encourage some of those vendors, those suppliers to actually make the changes that we're entirely dependent on them for. They're only going to make those changes if they see that we as the purchasers of their solutions actually care about having quantum resistant crypto. I also really encourage you to get hands-on with quantum-resistant crypto. I called out Open Quantum Safe as an open-source project providing implementations for you to work with, to experiment with. Also called out things like Firefox, Chrome, and others that are starting to bake some of those algorithms in. Really, really worth exploring that and becoming familiar with those. A reason being is that until we do some testing, we might not find some of those incompatibilities that start to come out as we start to do that migration. Key here is also looking at what is the level of support within our security technologies. Can our security technologies actually understand some of these quantum-resistant algorithms in the sense of things like our sensors, our network sensors, our scanners across our environments? So, wrapping up there, clearly quantum computing poses a long-term threat. But I would encourage you not to keep kicking the can down the road because doing that migration to quantum-resistant crypto is a long-term activity. Certainly there's no panic. And if you're still struggling with SQL injection on your public-facing web apps, please fix that first and then come back to post-quantum crypto, right? So let's be fair in terms of prioritization. And also, please keep an eye out for some of that fear, uncertainty, and doubt that some of our vendors and some of the media may portray. I've got a couple of other links up there to some further reading in terms of quantum risk report. Cloudflare have published some really awesome technical information on implementations. And of course, there's the Quantum Village that's also publishing some really great material on the topic. So with that, I think we've probably got a couple of minutes for a few questions. So if there's any questions, give us a wave and there'll be a microphone coming down.
Hello, you mentioned TLS support and Firefox, which sounds great, but the other on-the-wire one that I care about is SSH. Unfortunately, a completely different namespace. SSH2 algos and TLS 1.3 algos are not shared. Can you comment on the state of SSH? Is it behind? Is it anywhere?
Okay, what is the status of the SSH protocol as part of that transition to post-quantum crypto? I have not seen anything of any kind of material nature around implementing some of those post-quantum algorithms in SSH in a production sense. Certainly the Open Quantum Safe project have released some of those experimental binaries to run SSH using quantum-resistant algorithms. But if you go to their website, you'll see in a big red box, these are experimental. Do not use these for production. So you can start to explore them, but yeah, I'm not aware of any kind of production implementation as yet. Hopefully, though, this year, now that we've got those algorithms standardized, we should start to see a bit more movement. Any other questions? Go on then. Go for another one.
Sorry, I have got three. I'll just keep going. You mentioned harvesting. So is the implication there that anything using, let's call it classic perfect forward secrecy or Diffie-Hellman is potentially at risk there? And is there anything I can do today about that if I was extremely paranoid?
So yes, with the potential threat of harvesting attacks, it doesn't matter if you're using perfect forward secrecy, Diffie-Hellman. The fact that Diffie-Hellman is considered a broken algorithm in the face of a sufficiently powerful, cryptographically relevant quantum computer means, didn't give you anything, I'm afraid. Is there anything you can do today? Well, actually, now there is. Again, start using some of the algorithms that NIST are standardized. They're now available. They are now standardized. So, and they're starting to be built into libraries, so you can start to use them if you're getting a bit paranoid. Absolutely. And I think we had a question over here, so we'll give someone else a chance for a question. But I'll be around later for you to throw more questions at me if you like.
Hi, Andy. Thanks so much for your talk. I think with regards to an eye on the future and saying what we need to do for prep, looking at it from a hardware vendor's perspective, do you need to start worrying earlier?
Yes. Given the fact that hardware changes less often and it's more difficult to change hardware, right? Yes, absolutely. So any like IoT devices, any hardware devices, yeah, you want to bump those up the priority list in terms of at least making sure that you've baked cryptographic agility into them. You might not actually implement the quantum-resistant crypto today, but do you have the ability to, I don't know, push out a firmware update at some point in the future? Would that work? But yes, definitely prioritize the hardware. Cool. Right, so that's all the time that I have. But as I say, I'm going to be around for any more questions. Thank you, folks, so much for coming along.